So this is going to be going over how to do a Steam table problem. This is any problem where you have some properties of Steam, but you need to figure out the rest. And in this case, we have a nice little table here. So we'll start with A. We're given a pressure of 200 kilopascals and a temperature of 30 degrees. So what we want to do first is I like to start at the saturated water table. This tells us where we're at because we know if it doesn't match up with the information, then we're in compressed liquid water or superheated vapor. And if it does, then we know we're in the saturated state. So saturated water table, we go down to what we have, 30 degrees Celsius. We can see that the pressure we have is way above what it would be if it was saturated. So if we think about this logically, if the pressure is higher, then that means it's in the compressed liquid water state. So if we go down there, here we go. We can see that the lowest pressure they have is 5 megapascals. So we're actually going to go back to the saturated water table and use the liquid values. In this case, you can see the values are very, very similar for all this, but we're actually going to get slightly more accurate information because the pressure is a lot closer to 4 kilopascals than it is to 5 megapascals. So you can see here, yeah, we have 200 kilopascals, so that's way closer to this. So we have our specific volume right here, 0.001004. And we also have our internal energy, 125.7. Just make sure here you're using the fluid liquid values because you're going to be way off with the gas values. So we just fill this in here. Internal energy, I said that was 125.7. And we know that the phase is compressed liquid. Even though we are using the saturated water table, that's just because there's a little bit of gap between the two tables. So now going on to B, we have 270.3 kilopascals and 130 degrees Celsius. So again, we're going to start saturated water table. We have 130 degrees. And the pressure, we had a pressure of 270.3. So we can see that this is ever so slightly less than the pressure we were given. So what this tells me is that we're going to be right at the point where it's a saturated water, but it hasn't started to become a vapor yet. So we're just going to treat this as a saturated liquid. And we can see we have our specific volume, 0.00107. And internal energy, again, this is the liquid value here, 546.1 kilojoules. So we can just go back, fill those in. And 546.1. And we said this was a saturated liquid because it's right at the point where it's starting to become a vapor. So for the next problem, part C, we have our temperature, but instead of a pressure, we have this specific volume here. But we can still start the same way we have been, saturated water table. You can see that 400 is actually above the highest temperature value. And if we go to the specific volume here, you can see that the specific volume is way, way below what we have. So what this is going to tell us is that if we have a much greater volume, that it must be in a gas form. So this would make it a superheated vapor. So if we go down, superheated vapor, and we are looking for something with a temperature of 400 degrees and a specific volume of 1.5-ish. So we can see here, we need to keep going this way. 0.6, so we're getting closer. We have 400, a little bit too much there. So right here, we can see we have a temperature of 400 degrees Celsius, and then we have a specific volume that matches up exactly. So the pressure here is 0.2 megapascals or 200 kilopascals. And then we can take the internal energy here, 2,967 kilojoules per kilogram. So we'll just write that back here. We said this was a superheated vapor. We had, this is in kilopascals here, so we'll make sure we write 200 instead of 0.2. And the internal energy we had was 2,967.2. So now we go on to part D. In this case, we're given a pressure and a specific volume. So as we always do, we start in the saturated water table. This time we'll go to the one organized by pressure because that's what we have. So 300 kilopascals. So we can see our specific volume that we have is in between a saturated liquid and a saturated gas vapor. So we know that means it's a saturated mixture with some sort of quality, which we'll have to calculate. So if we go back here, saturated mixture, and we're going to have to find the quality here. So we'll do that in just a second here. So to solve for quality, we'll set up the equation specific volume equals the fluid specific volume, VF, plus the quality times the specific volume of the gas minus the fluid. You can see VFG equal to specific volume fluid minus specific volume gas. Then if we plug in our numbers, we have our specific volume of 0.5 meters cubed per kilogram equals 0.001073. This is the VF plus quality X times the difference in specific gas and specific fluid. Specific gas 0.60582 minus the specific volume of the fluid 0.001073. We can rearrange this, set X equal to 0.5 minus 0.001073, and then divide by the simplified difference in specific volumes. Once we do this, we should get a quality of 0.825. So now for internal energy, we can do something very similar, except the opposite, because we know quality this time. Same formula, internal energy equals the fluid internal energy plus the quality times the difference in gas internal energy and fluid internal energy. So we can plug in, we know all these values. The fluid is 561, quality 0.825, and the internal energy of the gas is 1,982 kilojoules per kilogram. So we're just going to solve, and we get 2,196.4 kilojoules per kilogram for the internal energy. So we can come back here. We got an internal energy of 2,000. 196.4. We found the quality to be 0.825, and the temperature was, where are we? 300. So we know it's going to have to be 133.5 degrees Celsius. So now on to E, we have this time a pressure and an internal energy. So, as usual, start with saturated water table. Pressure was 500 kilopascals. The internal energy is 5,000, or sorry, the one they gave us was 3,000, so it is above the maximum that it would be if it was saturated. So this tells us that it must be a superheated vapor. So we go to the superheated vapor chart. Pressure 500 kilopascals is equal to 0.5 megapascals. So we're going to be in here. Let's see. The internal energy is 3,000. So it's in between the 400 degree and the 500 degree amounts. So we're going to have to interpolate the data here. So we got to calculate the value between the two temperatures. We're going to start with the lower temperature of 400 degrees Celsius. And then we're going to add the difference in temperature. So that's 500 degrees minus 400 degrees over the difference in internal energies. And this is the maximum and the minimum internal energy that we're dividing by here, because after we do that, we multiply the whole thing by the difference in the internal energy value we have and the lower end of the internal energy value that we're looking in between. So we can see here, that's 3,129 minus 2,936, the max and the min for the values we're looking in between, times the value we have, 3,084, minus the lower end. If we simplify all this, we get a temperature 462.58 degrees Celsius. So now we just have to do the same thing for specific volume. We start with the lower end value, which in this case is 0.61731. And then we add to it the difference in values we're looking for, which is 0.71095 minus 0.61731 meters cubed per kilogram. And we're going to divide that by the difference in the lower and the higher end of internal energy. So 3,129 minus 2,936 kilojoules per kilogram. And we multiply the whole thing by the actual internal energy we have minus the lower end value. So 3,084 minus 2,963.7 kilojoules per kilogram. And if we do that, we should get a value, a specific volume, 0.67589 meters cubed per kilogram. So now we can come back here, write the values we got. We got 462.56 degrees Celsius. And specific volume, we got 0.67589. And again, this was all in the superheated superheated vapor phase. And after that, we are all done.